Alright, so what we're going to do here is we're going to look at functions. And we're going to begin functions with an idea of space. We're going to take space and we're going to put two number lines down. Now this idea was first articulated by Descartes. Descartes was known for the I think, therefore I am. What he did is he put a number line to represent the x-axis and a number line to represent the y-axis. And so along the number line, there are evenly spaced numbers that represent how far you move in the x direction and how far you move in the y direction. Now for right now, I'm just going to look at the positives. So everything over here is the positive x direction, and everything over here is the negative x direction, and everything up here is the positive y direction, and everything down here is the negative y direction. And what we can do is we can describe a point in space, right, a point, as two numbers, an ordered pair of numbers. Ordered pair, or sometimes called coordinates. And so an ordered pair is we always write the x value first, followed by the y value. And so in this case, the x is 3 over in the x direction and 1 up in the y. So this is 3, 1. Now what Descartes was trying to do was he made these at right angles to each other. So however much I move in the x direction, it doesn't affect the up-down. And so you can talk about the two directions separately and keep the pairs together. Because what he wanted to do was he wanted to borrow from triangles, because triangles had some very good knowledge. Let me make a triangle here. So I'll make my other point right here. And so this point's at 1, 2, 3, 4, 5, 6, 7. So it's 7 in the x direction. And 1, 2, 3, 4, 5. I don't want it at 5, I want it down 1. Let me see. 1, 2, 3, 4. I want it at 5 and 4. Or 7 and 4. So we'll make it down there at 7 and 4. So let's do that. Let me clean off the other one here. I don't want that one. Yeah, we'll do a little cleanup here. And so I have 2 points. And the geometry Descartes was going to borrow was Pythagoras. He was going to borrow ideas from Pythagoras and use them to help talk about things mathematically. And what he was borrowing from Pythagoras was the idea that if these things were at right angles to each other, we could borrow right triangles. And what we knew about right triangles from Pythagoras was these were at a right angle to each other. We had the Pythagorean Theorem, which is this leg, the relationship between the two legs, the parts that make up the right angle, and the hypotenuse, what was opposite the right angle. And what happened was the square of the hypotenuse was equal to the sum of the squares of the legs. Well, what this does is if I'm at this point and I walk to this other point, the hypotenuse is the shortest distance to get there. And so this became a way of measuring the distance between 2 points. And that's what Descartes wanted to borrow here, was that distance would become natural to putting things here, because everything parallel to this side of the right triangle talks about the change in the x direction, and everything parallel to this side of the right triangle talks about the change in the y direction. And so we can talk about the points as if they're part of a triangle. And so this let us start doing some complicated maths with the ordered pair and having some meaning to the maths. So let's look at ordered pairs in general and see what happens with them. I'm going to clear the screen here and move down a bit. So let's take our XY axis and just get some orientation on it. And then we'll start using those triangles underneath it, and we'll make everything work for us. Now what happens is that we have quadrants. When I cut space with an x-axis, it gives me a positive x and a negative x half. If I cut it again with a y-axis, I get a positive y and a negative y half. Positive x is over here, negative x is over here, positive y is up, negative y is down. And so everything over here, the ordered pair here, all the x values are positive, and all the y values are positive. And we call this the first quadrant, because everything's positive. We tend to start a lot of our work in the first quadrant because we can talk about positive only values. Now if my x values are negative, notice how I'm keeping the ordered pair. I write the x first, then the y. And my y values are positive. It's over here, and we call this the second quadrant. So notice we're moving counterclockwise. And this is a right-handed system. Right-handed systems move counterclockwise. The idea is if you take your right hand and you lay it so that your fingers in your right hand are pointing on the x-axis, and you turn, going through your quadrants, your thumb would point outwards. And there's a mathematics to that that we don't need to delve into, but we're going to go counterclockwise here. And so if my x is negative and my y is negative, that's the third quadrant. And if my x is positive and my y is negative, that's the fourth quadrant. And so we have our ways of talking about anywhere in space. And everything is measured from this spot here, called the origin. And the origin is at 0, 0. And so we measure relative to the origin. Now, the game we're going to do here is we're going to look at ways that we can talk about graphing equations in two variables. So if we have equations in two variables, we're going to start talking about things where we have two values. And what we tend to do is we tend to write our equations in two variables in the terms that y equals something. And we do that, I'll just put a general version of one here. Y equals something times x plus b. And our variables are x and y, and these are constants that have meanings, things that don't change. And what we'll start to think of is, we'll sometimes also say this is a function form, where we'll say y can equal the function of some variable in x. And both of these things fall into graphs nicely for us. A functional form says, and I'll do it like this, f of x equals, and I'm going to give an actual example right now. I'm going to say 1/2 x plus 3. And we can think about values falling into here. I can put into here some value, like f of 0. And when I put in f of 0, wherever I see x, I replace it with 0. Right? So my function will say, hey, here is my rule for what the function is. When you give me a value for x, I spit out an answer. And so f of 0 is equal to 3. And so what happens is this side, the left-hand side in this case, or the function, is dependent on the values of x. So we call it the dependent variable. And x is allowed to move freely, so we call it the independent variable. And when we plot these things, we plot them on an xy axis, where x runs across the horizontal and y runs on the vertical. So let's take what I wrote here and see what this looks like. So what we'll do is we'll make a table of values. I will put in some values for x, and I'll see what comes out on the y side. And so I started with 0. I put in 0, and I get 3. Let's put in 2. And so if I put in 2, I'll write this in blue. So f of 2, I'll write it down here. F of 2, wherever I see x, I replace it with 2. So 2 times 1/2 is 1. That's going to equal 4. And let's do one more. Let's do -2. So f of -2, wherever I see x, I put in -2. And so I get -1. -1 plus 3, which is 2. And so now I can plot these points. I can find these ordered pairs and see where they are in my space. So if x is 0, I'm up 3 on the y-axis. So I'm here, right? Because x is 0, I get 3 for y, and that's the point 0, 3. Now if x is 2, I'm up 4 on the y-axis, so I'm here. And if x is -2, I am at 2. I'm here. And if I look at these together, no, that's not quite the line I wanted. I get this line. In fact, this function is the graph of a line, and any point on this line this point here is what happens when we 1, 2, 3, 4, 5, 6. We put 6 in there. So we put f of 6 in. And so I get 1/2 times 6 plus 3, or 3 plus 3, which is equal to 6. And 1, 2, 3, 4, 5, 6. Hey, that is the point 6, 6. So anything on this line is this function. And this is what Descartes' graph lets us do. It lets us talk about two variables where we can see how they move through space. And when they move through space like this, any point in here is a solution to our function. And so notice how I did this. I had my space and I put even markers on it. Graph paper works for that. I labeled this one x and this one y. Where they meet is 0, 0. And then I take the rule I have for my function and I plot some values of x on it. And when I plot those values, I get points. Now in this case I connected these points together because this is a linear function. And well, let's look at the linear function in general. Functions in the form of some number times x plus some other number are said to be linear. And the key is that the variable x is to the first power. Right? We don't write first powers. And f of x is also to the first power. We could write this as y equals mx plus b. And that's an equation of a line in slope-intercept form. What happens is m is the slope of the line. It talks about how much it changes in the y direction, over how much it changes in the x direction. And so if we could take any 2 points and do the change in the y minus the change in the x, we get the slope. Or we can think of it as the rise over run. Right? And there's some repetition in the ideas here. And so I could think about it as, if we look at this one, it had a rise of 1 and a run of 2. And so if I was here, I'd rise 1 and I'd go over 2, and I get my next point. If I was here, I'd rise 1, I'd go over 2, I'd get my next point. Rise 1, go over 2, I'd get my next point. And so on. We do these little rise runs all the way across. And so linear functions have this form. Let's look at something that's not linear. Let's look at a function of x, or we could say y equals this, right? I hope we'll see that we can exchange these. As long as there's no power to y, we can use functional form or y equals form. And what we're going to do is we're going to do one of our quadratics. We're going to do x squared. What x squared do I want to do? I'm going to do 4 minus x squared. Now this was similar to our quadratic equations that we did before. And we could find solutions to these if we could set this equal to 0. Well, let's see what that means graphically. So what I'm going to do is I'm going to make a table of values. I'm going to write down possible x values and possible y values. This is x and this is y. And so what we'll do here is I'll make a table of x values. And so first off, I always like doing 0 for x. So I put in 0 wherever I see x. So 4 minus 0 squared. Right, this will be f of 0, which is equal to 4. Alright, well then what I'll try next is I'll try 1. And so I'll change color here. So I put in 1. Wherever I see x, I replace it with 1. So that's 4 minus 1 squared, or 3. And I'll do negative 1. I like going back and forth with squares, because f of negative 1 is 4 minus negative 1 squared. But negative 1 squared is 1, and I get 3 also. And I'll do one more. I'll do negative 2. And so f of negative 2 is 4 minus negative 2 squared. Well, negative 2 squared is 4, so that's 0. And so I'm going to, oops, that's 0. So I'm going to plot these points. I think I'll make it bright yellow. And so the first one, I have at x equals 0, my y is 4. So I'm going to come up 1, 2, 3, 4. So I'm going to be here. Now when x is 1, my y is 3. Right? I'm working my way through each of these points. When x is 1, y is 3. And when x is negative 1, y is also 3. And when x is negative 2, y is 0. And I will say there's a symmetry here in this case. When x is 2, y is still 0. And what this does is it creates a thing called a parabola. And parabolas have this shape on them. And they have a special point called the vertex, which is the center of an axis of symmetry. And we'll look at these parabolas in a little more detail, but notice what we were able to do here. We were able to, by using a table of points, shape the behavior here. We saw these early points, and we saw that they were building a symmetry on them. And we were able to make it show a little more detail. So this table of points helps us get a shape, and a shape gives behavior. And we can notice the behavior of this is linear. It makes a line. When we see x to the first power in a functional form, we get a line. And so we know it's going to move like this. When we see x squared, we get a parabola. And there's two possibilities. If the number in front of the squared part is negative, it's concave down, it points down, and the vertex is a maximum. But if we have a function where x, whoops, I hit the black, let's go in here, and I'll just put x squared, we'll say f of x equals f squared, I'm over in the corner there, f of x equals x squared. That's a parabola that starts here and shoots up like this. And so if the number in front of the squared is positive, it's concave up, and the vertex is a minimum. We have packed a load of information into the visualization of it. We're letting the visual graph tell us what the function is doing. By taking these things and plotting the points, we can talk about behavior. With a line, we can talk about how it's rising and falling, and that relates to the slope. We can talk about where it intercepts the y-axis, which is the y-intercept here, which in the case of ours, right, the y-intercept was 3. So when x is 0, it's intercepting at 3. And so we have some information here. For quadratics, right, we get this vertex, and we get a min or a max. And we get this curved behavior from it. I want to look at this one right here, the 4 minus x squared, though, and I want to focus on these 2 points. When x was 2 and negative 2, this thing equaled 0. And I want to think back to our quadratic equation. So in the quadratic equation that we had previously, we said when ax squared plus bx plus c equals 0, and we had it in this form, we could get the roots, the solutions. And we did that using the quadratic formula. We said x was equal to negative b plus or minus b squared minus 4ac over 2a. Well, let's do that for 4 minus x squared. So we're going to look at 4 minus x squared, but we're going to ask when it equals 0. Well, notice when it equals 0, it's going to be the values that cross the x-axis. And so we are looking for these 2 points that cross the x-axis. And so we'll set this equal to 0, and I'm going to rearrange this. I'm going to put minus x squared out front, and I'm going to put plus 4. And so I'm going to say that a is equal to negative 1, b is equal to 0, and c is equal to 4. So I'll come over here, and I'll put this into my quadratic equation. That'll give me minus 0 plus or minus 0 squared minus 4 times 4, all over negative 2 times, whoops, not negative 2, 2 times negative 1. It's going to be negative 2. And so I get, missing a minus sign here. Oh, yep, there's a negative 1 here, so I need a negative 1 in there for AC. There we go. And so I get negative 0 plus or minus square root of 16 over negative 2, or I get plus or minus 4 over negative 2. And so when I do the positive 1, I get negative 2, and when I do the negative 1, I get positive 2. And my solution set happened to be these 2 points. And that was that at the time, that was what Descartes was going for. He was going for ways of finding solutions where we could find where it crosses the x-axis. But in exchange for that, we got so much more of the behavior that these functions were doing. All right, we're going to build tables and graphs. And we're going to use the values we can get to create graphs a little more. But I want to introduce why these things were inventive and how useful they can be.